Okay, let's take a look at end behavior. Now, lots of people have a little bit of difficulty with end behavior, and I cannot stress enough how much a table of values is important. I literally have it taped to my wall at all times. Whoops, it's taped to some other things. A table of values at all times. Because so many times we just get used to using our graphing calculator and forget about the basics and forget how to just do a table of values in our head and understand so many parts of math. Outside of that, let's take a look at the notes. 3.4, end behavior. We're going to take an example of a positive number, a positive number with a variable to an even exponent. So we've seen a lot of those before. Let's take a look at a positive y equals a positive 1x squared. And we know what that looks like. So remember, 0 squared is 0, 1 and negative 1 both squared are 1, and 2 squared and negative 2 squared are both 4. So we have our parabola. Now, all I really care about this definition is if I have a positive x to the even. Because if I have a positive x to the even, I know that in quadrant 1 and in quadrant 2, both those arrows go up. So if I ever in the future see a positive x to the even, I know on both sides I go up and up. So if you remember in grade 10, we did y equals x and it was a line, and then we did y equals x squared. And then remember in grade 11, we put a negative in front and made it go downwards. Let's go down the page in the notes and let's take a look at a negative number, x to the even. So I know that that parabola has simply, I'm going to write out the equation first. Y equals negative 1x squared, which is a parabola that has been vertically reflected, opening downwards. And I know that any negative x to the even opens from quadrant 3 to quadrant 4. So in the above example, any x to the positive x to the even, positive x squared, positive x to the 4, positive x to the 6, all open up like this. Any next negative x to the even, negative x squared, negative x to the 4, negative x to the 6, all point downwards. So anytime you see a positive x to the even, we're going to get arrows going up and up. And anytime we get negative x to the evens, we're going to get arrows going down and down. Notice in the notes I've done tables of values, and you can see substituting x values in, seeing where those points on the graph are going to lie. So now let's see very similar examples. Let's see a positive number, x to the odd exponent. So let's go for something like y equals positive x cubed. So we haven't graphed that much. But 0 cubed is 0, 1 cubed is 1, 2 cubed is actually 8, so it's going to be way up there. Negative 1 cubed is negative 1. And I can draw that graph. Feel free to graph it on your graphing calculator. Look something like that. So I know that if I have a positive x to the odd, like positive x cubed, I know that I start from quadrant 3 and end in quadrant 1. X cubed, x squared, x cubed, x to the 4, x to the 5, x to the 6, x to the 7, x to the 8, etc. So now let's take a look at a negative number, x to the odd. And let's go for something like y equals negative x cubed. Well, I know that that would be a vertical reflection, whereby now, I'm going to draw the x-axis a little bit higher. So now if I do a table of values, or I do a vertical reflection from the graph above, I multiply all my y values by -1, and now my graph is a complete and vertical reflection. Feel free to graph more of that with a table of values or with your graphing calculator. But I know that if I have a negative x to the odd, I know my arrows always go from quadrant 2 to quadrant 4. And any negative x to the odd, negative x to the 7, that is where my arrows go. Positive x to the 5, that's a positive x to the odd above. This is where my arrows go. Now let's work through a bunch of similar examples. Okay, we're going to go quickly now. So, same title as the last one. We now just simply have just a few equations with their graphs. Let's take y equals x squared, as we've seen before. Well, we know that the y equals a positive x to the even. And I know that a graph more steep, like positive x to the 4, or another version of x to the 4 with a couple of w's, as seen in the notes. All I know is that if I have a positive x to the even, I go from quadrant 2 to quadrant 1, again from quadrant 2 to quadrant 1, up and up. And what if I do a vertical reflection and do y equals negative x squared? And I take the graph and I shift it, go downwards. Well, that's a y equals negative x to the even. And other negative x to the evens, like negative x to the 4, a little bit steeper. And another version of x to the 4, y equals x to the 4, excuse me, negative. I don't like it when I do that. I'm not going to do it in front of you. Negative x to the 4 plus or minus ... But all I care about is if I have a y equals negative x to the even, I know that my arrows go down from quadrant 3 to quadrant 4, again, down and down. We're going to use that concept again. So, likewise, y equals x cubed is this graph, which you can graph with the table of values or with your graphing calculator. Excuse me. Yes. And this is a y equals positive x to the odd exponent. And we know that similar graphs to that are y equals positive x to the 5 and another version of x cubed with some x-intercepts, a positive x cubed, plus some other things. Now, I know that we're going from quadrant 3 to quadrant 1, again, quadrant 3 to quadrant 1, if we have a y equals positive x to the odd. Now, what if we vertically reflect that like we did before and do, and do y equals negative x cubed? Well, that graph, feel free to use your graphing calculator or graph it with a table of values. And we now simply have a y equals negative x to the odd. So we know that if we have a graph like y equals negative x to the 5, it looks very similar to y equals negative x cubed from above, just a little bit steeper. Or some other version of y equals negative x to the 5, or y equals negative x to the 3 plus some other things. And again, we may have some more x-intercepts, but the main point is that if the arrows go from, if we have a negative x to the odd, the arrows go from quadrant 2 to quadrant 4. Again, quadrant 2 to quadrant 4. We're going to use these applications on the next section when graphing, still in this video to come. Okay, so let's take a look at a couple of graphs. So from grade 10, we have y equals x minus 2, and I'm just going to put it in factored form. And that's why we have a y-intercept of negative 2 and a slope of 1. Notice we have an x-intercept of 2 if I set my factor equal to 0, and we say that factor has an exponent of 1. We then went on to grade 11 and saw equations like y equals x minus 1 and x minus 3. And we knew we had x-intercepts at those factors, so if I set those equal to 0 and solve, I get x minus 1 equals 0, so we have an x-intercept at 1 and an x-intercept at 3. And I'm going to forget about the y-intercept for a second, and the vertex, and I'm just going to draw that graph. But I know that if I have exponents of 1, like I did before, those exponents of 1 have x-intercepts where we go straight through the factor and come up through the other. Then in grade 11, we saw if we have a single x-intercept, like the equation y equals x minus 2 squared, whereby we have an exponent of 2 and we see a new thing happening. We bounce off the x-intercept. Interesting. Let's see another. So we've got x-intercepts of negative 2, 0, and 2. Therefore, the equation would be y equals our first x-intercept. Let's go for the one at 0 first. It's just going to be x. I could say minus 0. And then one at negative 2, so x plus 2. And then one at 2, so x minus 2. And all of those have exponents of 1. So they're going to go straight through. And if you remember from end behavior, if I FOIL this out, I get x cubed. So my arrows go down this way and up this way from quadrant 3 to quadrant 1. Then I can draw the graph up through my x-intercept, down through my x-intercept, to up into the first quadrant. Because if they have exponents of 1 in blue in the top left, and in blue in the top right, if they have exponents of 1, all of the x-intercepts go straight through. And again, if we have an exponent of 2 in blue on the left, that means that we have a factor that bounces off. So now let's see another example of one that goes straight through and bounces off. So let's go for a graph with an x-intercept at 1 and negative 1, seen in the notes. Pardon the rest of it, and that would be y equals, we have x-intercepts at, negative 1, and we bounce off at 1. Therefore, the x-intercept of negative 1 has a factor of x plus 1, and the x-intercept of 1 would be x minus 1. Now it bounces off, so it would have an exponent of 2. So the factor with an exponent of 1 goes straight through the x-intercept, but the factor with an exponent of 2 bounces off the x-intercept. Okay, so that was grade 10 and 11, going straight through and bouncing off. Now, let's take a look at an interesting chair shape that we've seen before. So we have the graph y equals x cubed, which goes down and flat and up. And I know that it's a positive x cubed, so that's where my arrow tips go. And I get this interesting, if I have a factor has a exponent of 3, I get this interesting chair shape happening. So let's see one more example of those. So let's go for y equals, that's in the location of the video. I'm going to take this question off to the right in the way of the video, and I'm going to do the new question off to the left. Excuse me, I'm a rookie. So we are going to draw a graph, and we're going to say y equals x plus 2 to the exponent of 1 and x minus 1 cubed. I hope that didn't hit the video. I'm going to move this equation off to the left. So I have x-intercepts at -2 for my factor of x plus 2, and I have x-intercepts at 1 for my factor of x minus 1. Now, how is this going to work? Well, I know that my x plus 2 has a factor of 1, so it's going to go straight through, so I'm going to draw a little x. And then I know my other one has a chair shape, so I'm going to draw a chair shape in both directions, and you have to use a different color if you want to successfully do it without it looking like two parabolas hitting each other. And then I know if I have y equals x and x cubed, I have positive x to the 4, so my arrow tips go up and up from quadrant 1 to quadrant 2 to quadrant 1. Then I simply draw my graph. So I've done it a lot better in the notes, but we come down from the arrow, straight through, back up, chair shape, and way up. Now don't have to hit the arrows, but we should be generally going in that direction. So now let's put it all together into a graph. Okay, let's graph the equation y equals x, open bracket, x minus 2 squared, open bracket, x plus 2 cubed. So the first thing I'm going to do is draw the graph. Now, in the notes, we've got multiple graphs showing each of the individual steps one by one, but I'm just going to draw one massive graph. So the first thing I'm going to do is I'm going to take this x, and I'm going to multiply it by this x, which is to be squared, multiplying it by this x, which is to be cubed. So y equals x times x squared times x cubed. And I know that I get y equals a positive x to the 1, 2, 3, 4, 5, 6, which is a positive x to the even. And I know from the previous examples, if I have a positive x to the even, like positive x to the 6, I start by putting my arrow tips going up and up. Then if I set each of my factors equal to 0 for my x-intercepts, I get x equals 0, x equals 2, and x equals -2. And I can put those points on the graph at 0, 2, and -2. And then I want to mark my behavior. So, you know what? Let's find the y-intercept really quickly. Y-int. Well, I know that my y-intercept has an x value of 0. And you know what? Feel free to read through the notes on how I substituted 0 in for x. But look at the graph. The y-intercept is 0. We don't need to find the y-intercept if we already found the x-intercept to be 0. Okay, so now we're going to talk about multiplicity a little bit more. So the x has an exponent of 1. So its factor goes straight through. And I do an x. I did it a little bit differently in the order in the notes. Now let's look at the factor of x minus 2. Because it's squared, it bounces off. So at the x-intercept of 2, I'm going to do a u-shape. Two u-shapes, one on top of each other. Now we have the x-intercept, x plus 2, and we're going to do a chair shape. It's difficult to do without two colors because it looks very much like the other case. Now, we just simply want to start from one of the arrow tips. We want to come down. We want to do a chair shape. We want to come back up through, and then we want to bounce off. And notice I didn't care about hitting that other arrow. Just making sure it looks approximately like that. Start from an arrow, do a little chair shape at your x-intercept of -2, go straight up through your x-intercept of 0, and then bounce off your x-intercept at 3. We're going to find this point and this point in calculus, or if you want to use your graphing calculator. So where did this equation in the beginning come from? Well, it must have been some long y equals x to the 6 plus a bunch of other stuff. We could FOIL that thing out, expanding it by distribution, and we could get exactly what it was, and then we could reverse the process. But remember, we would start off by doing the potential factors of the last thing. Then we would do synthetic division. Then we would find out what all of our factors are. Then we would line them all up. And in blue, big blue at the top, we would get our equation to be worked through. I couldn't fit all of that on one page. Now we can fully graph, fully factored, higher degree polynomials, because in grade 10 we did lines, and in grade 11 we did parabolas, and now we've seen cubed, and to the 4, and to the 5, and all sorts of other versions of those with W's, etc. I really want you to think about some of those monkey positions, so when you're in the test and you're thinking, what do these things look like? Well, they're all sorts of things. Straight lines, U-shapes, W's, funny looking S's, more funny looking S's, and all sorts of other combinations that we can only do with limited joints.